Now we are in second session of quantum computing track. We have another eminent speaker in this session. Being her student, it is great pleasure for me to introduce my madam, Professor Shushmita Shurkole. She has received the BTech degree in Electronics and Electrical Communications Engineering from Indian Institute of Technology, Kharagpur, and the PhD degree in Computer Science and Engineering from Jadavpur University, India. She has been a faculty member in the Advanced Computing and Microelectronics Unit of the Indian Statistical Institute, Kolkata, India since 1999 and is presently a professor. During the period 1993 to 1999, she was a reader in the Department of Computer Science and Engineering of Jadavpur University. Prior to that, she was a postdoctoral fellow at University of Nebraska-Lincoln and a research assistant at the Laboratory for Computer Science in Massachusetts Institute of Technology. She was also on sabbatical at Princeton University and Intel Corporation, USA. Her research contributions are in the areas of electronic design automation for VLSI physical design, fault modeling and testing, synthesis of quantum computers, and graph algorithms. She has co-authored several technical papers in leading international journals and referred conference proceedings, and a chapter in the Handbook on Algorithms for VLSI Physical Design Automation. She was the technical program co-chair of the 18th International Conference on VLSI Design 2005, the 11th Symposium on VLSI Design and Test 2007, IS VLSI 2011, and has served on the program committees of several international conferences. Among other awards, she was the recipient of the President India Gold Medal at IIT Kharagpur 1980, IBM Faculty Award 2009. Her today's title of the talk is Challenges of Quantum Computing. Now I would like to request our Honorable VC Sir to say few words to our Professor Shushmita Shurkole ma'am.
So really, I do not have much to say. Actually, Professor Shurkole, whom I call as Shushmita Di, he's a very well-known figure in quantum computing and means other CAD, VLSI CAD areas. So I am sure that with her knowledge and with her experience in this field, the audience and the participants will get a lot of insight into new research areas and understanding of new concepts. So Professor Shurkole, you can start, I believe.
Thank you very much, Topolina, for your kind and rather long introduction. And thank you, Indranil, for your very warm welcome. It's a pleasure for me to speak at this faculty development program. Let me share my screen. Is it visible?
Yes, ma'am, it is visible.
Okay. So, Professor Indranil Sengupta, whom I call Indranil, did a wonderful work in his talk. He introduced reversible computing and quantum computing. So the agenda today, the first bullet, of course, most of it has been covered by Indranil. Just for the first timers, maybe a quick refresh. And then what I'll focus on is a little bit of delving a little bit in detail, just a little bit, in the quantum algorithms, the main three which led the researchers to sit up and look into this area, which has a lot of power over our existing classical computer for certain problems. And then I move on to being in the area, having been working in the area of computer-aided design for electronic design automation. My, my journey in the area of quantum computing has been related to synthesis. So what I would like to present is what are the challenges, just a bit, because there are other speakers in this workshop later on who will go deeper into the various synthesis methodologies. So instead of going into the methodologies, I will just focus on what are the challenges, how is it different from electronic design automation, what needs to be kept in mind. Some of the topics, some of the issues were pointed out by Indranil. And then how can we design quantum algorithms with what we have now, the limited capability quantum computers that we have now, what can we do with them? And as you know that quantum systems are noisy, which leads to errors. So how can we, what are the different techniques in which people are trying to tackle these? So my focus is in that area, and recently I've been working with my students. So I don't know whether you can see the acknowledgements, Gurjit and Devashmita, who are working in these near-term quantum computing areas. So I'll share some of the works that we've been doing, and particularly because this being in the this being organized by the Department of Computer Science, I would like to point out what computer scientists and engineers can look forward to. We already know about the major drivers. There have been algorithmic limitations, and because of superposition and entanglement, which is unique to quantum mechanics systems as opposed to our classical systems. It's a matter of scale, actually. The classical systems, as you know, the Newton's law of gravitation and Einstein's law of gravitation. The difference comes in the scale. So at very small level, the laws are different, and that's where quantum mechanics came in the early 20th century. And so on the figure here, you can see Charles Babbage's electromechanical computer. Then we had, from the 80s onwards till today, we have
Sorry
this.
for the interruption, madam.
Yes.
Madam, slides are visible but not in slideshow mode. Only first slide we are viewing.
Oh, is that so? So let me try sharing again. How about now?
Now it is fine, ma'am.
Okay, thank you for pointing it out.
Thank you, ma'am.
Right. So, apart from algorithmic limitations, there are also hardware limitations. Computers are getting smaller, and they're reaching the point where classical physics is no longer a sufficient model for the laws of physics. Today we have 14 nanometer transistors, which are as small as 14 nanometer and even 10 nanometer in 2021 now. So quantum mechanics is coming in, and therefore both the problems we would like to solve and the machines on which we want to solve them, they have their limitations. And so from the domain of semiconductors, we have moved on to the domain of quantum computing. A little bit of history. Alan Turing came up with the idea of computing. And Richard Feynman, the famous physicist whom we already talked about, in a talk at MIT, And I would like to share this anecdote. I usually do in most of my talks on quantum computing. I being a graduate student at MIT at that time, I was present at that talk. And he said something which didn't really sink in. And what he said was, there's a lot of room at the bottom. That means you look at quantum mechanics to be able to solve problems such as simulation of large dimensional quantum mechanical systems such as in quantum chemistry, quantum physics, and so on. And very soon, another theoretical physicist in UK, David Deutsch, sorry, he toyed with this idea. He brought this forward and first gave the so-called first quantum algorithm. But it didn't impress too many people till Peter Shor in 1996-97, another mathematician, solved the factorization problem, that is, given an integer, how do you factorize it to its factors in polynomial time? Because in classical domain, it was shown that you cannot do better than exponential time unless certain theoretical concepts known as the class P and the non-deterministic class of polynomial time algorithms and the non-deterministic class of polynomial time algorithms are equal, which is very unlikely. So since then, some of the experimental physicists had started on working, and the initial experiments were with nuclear magnetic resonance, NMR spin, and but only 4-5 qubit, very small systems covering almost an entire big room were being built up. In fact, our own at IISc Bangalore, one of the very famous professors in the Department of Physics, he also had NMR-based quantum computer systems. It was in 2012. It was recognized that the Nobel Committee recognized these two experimental physicists who actually proved that you could measure and manipulate. Manipulation is what we need for our quantum to design our quantum algorithms. So experimentally, they proved that this was possible, and this was recognized. So you have seen quantum states. So it's usually because it's a continuum of states in what is known as a Bloch sphere. So what you saw as a combination of the 0 state and 1 state with a linear superposition of that. So these weights that are used to superpose or combine two of these states, which are known as the basis states. So why is it called basis? Because you see, you have the whole continuum space, the infinite number of states in this space on the unit sphere. Any point on the surface of the sphere can represent a state of the quantum system. So a single qubit individual quantum system can be in any of the states which are represented by a point on the surface of the sphere, this unit sphere. But we don't need to get disillusioned by the fact that there are infinite number of states and how can we represent them and how can we operate on them. The nice thing is that this state space can be represented in terms of a finite number of basis states. This comes from algebra. I won't get into that. But those of you who are interested, I would really recommend that you look into it. It's very nice algebra and very nice mathematics. So, therefore, for a single system, for a single qubit state, only two basis states are enough to represent any state in this sphere. And you can see that if you are representing this state in terms of a vector in the unit sphere. So the zero state, the pure zero state, is represented by this purple vector here. The pure one state is represented by the down vector over here. And remember the Hadamard operation for superposition, equal superposition of these two states. If you apply that, so if it was a zero state to start with, and you apply the Hadamard state, a Hadamard gate, then what you would get is this equal superposition of the states 0 and 1. And so this is your state vector after you operate with the Hadamard. Similarly, if you apply Hadamard operation on the one state, you get the following superposed state. And note, the reason I'm going into this detail is that these are equal superposition but with opposite phases. So this phase is a very important factor in quantum computing, which is made use of in many quantum algorithms. So this was with a single qubit, and as Imran pointed out, if you have n qubits, then because of these Hadamard, so it's a single qubit operation, but it can create superposition of all 2 to the power 4 possible states. You will see more of this when you get into the following lectures in this workshop. And as a result, if you actually, now that the IBM quantum hardware is available to all over cloud, the 17 qubit, if you actually implement this and then measure the output over here, now see, with 4 qubits you can have 16 possible states, and ideally they are with equal probability any of these possible states. So if you keep repeating measuring, if you keep repeating this experiment, like you set all zeros here, apply Hadamard operation, and then measure, over here, then if you do enough number of trials, you will find that in almost equal probability, you will find that all these 16 states are being represented. So it's about 1/16th probability that you will get in any of these states. Now, if you apply a different kind of gate, which is a rotation gate, so this Rx means rotation about the x-axis of the block sphere, and the parameter here is the angle by which you are rotating. So if you start with a 0 and you apply Rx pi by 3, then this is the state vector, this is the state in which you will end up. And notice that this is again on the block sphere, but you will have some complex values to represent the, so it's not equal superposition in that sense. So it is, because it's pi by 3, it will have more of state 0 than of state 1. And if you started with 1, it's just the opposite. And if you repeat the same operation with 4 qubits, there are 16 possible states. And if you measure, because you are doing pi by 3, it's with a very high probability that you are likely to get the state 0, because you started with all zeros, and it's with a high probability that you will get a state 0, but it's not equal probability as expected. Okay. Similarly, the CNOT gate you heard about, and this is the matrix that Professor Shengupta showed you. The unitary, it's actually, CNOT is also reversible. You don't see any complex numbers here, but for the rotation gates, you will have complex numbers. So the CNOT, if it is a 0 qubit for the first qubit and 0 qubit for the second qubit, then what you get is no change. Sorry, the first qubit was 1, the second qubit was 0, so therefore CNOT was 1 here and 0 here, so you would get 1, 1. This is what is happening. You already know about this, so I'm going to skip this part. And the quantum circuit that you've also seen this, and we will see this later on because this is a particular circuit which I will actually use when I'm talking about quantum algorithms. Okay? It's a sequence of actions of its combination. There is no fan out, there is no feedback, but it is a sequence of actions. So I'd like to remind you that although we are representing the circuit like this, that we have these gates and we have these lines connecting these gates, just as we do for our schematics for our electronic circuits. In quantum, actually, what happens is if you look at the quantum, so if you look at an electronic chip, you will actually physically be able to identify the locations of the gates. You won't be able to, locate the, what should I say? So the charge carriers which take the feed into the gate and take the output of the gate to the next one, okay? Because they are electrons or holes in semiconductors. Okay? So you can't locate them. What you can locate in the electronic circuit are the positions of the gates, and that's why when you design, when there is an optimization problem for electronic circuits, you want to minimize the number of gates so that the area that the chip, the size of the chip is not too high, and also you want to minimize the number of steps, number of gates through which it goes, because that tells you when the time that the time required to complete operation. So that is also true over here. So here these black lines connecting from a gate to the next gate is just a representation of time. So time is flowing from left to right, but it's reversible. You can also flow from right to left and you will get back. So that's the nice thing about quantum circuits. And what you have physically are the qubits. So that is why you want to minimize, when you realize a quantum circuit corresponding to a quantum algorithm, you want to minimize the number of qubits. And of course, you want to minimize the number of gate operations in parallel, that is, which is known as the number of levels, so that the operation to complete the execution for an algorithm is fast enough. In the case of electronic circuits, which we are very familiar with, time is important because we have been greedy. We want faster and faster speed, and of course that has certain other implications also. Now, the faster speed is related to what is the maximum amount of time, or if it is digital, the clock ticks that you would need. So the clock frequency has to be such that the clock period is larger than the time of operation of each of the combination gates. So that is how they are related. Now, in quantum circuits, what happens is that these qubits, as you know, they are supposed to be in closed environment without interaction with the outside world. Otherwise, the state is going to change, because the outside world is acting on the state, means that it is almost like an operator, and usually these operators are applied in reality in terms of applying electromagnetic field, depending on how you realize your qubit. Okay, so now if I don't apply any field, I would ideally expect the qubit, if it is somehow initialized to, let's say, one of the basis states, to remain in that basis state forever. But that doesn't happen. there is, I mean, in reality, just as you don't have a ideal point or an ideal line, everything has a width. Similarly, in quantum systems also, ideal, or you, in physics you don't have ideal vacuum. So here also, you after some time, there is a slow degradation of the state, and beyond a certain point, beyond a certain time limit, the state of the qubit changes so much that if you, whatever your intended operation was, if you perform that after that time period, then you will get an erroneous output. So that is known as what is called the decoherence time. So when you are designing a quantum circuit, you want the number of levels, and a certain time is associated with the gate operation. If you multiply that, you want all of that to be less than the decoherence time. Okay? So that is why there is a great challenge for these experimental physicists. Google has announced its 72 qubit machine in 2018, but it is still fighting to beat this noise. Okay? And how do we, the purpose of designing quantum algorithms is to start from something. So even in classical algorithms, what do? We have an input, okay? And we perform a sequence of operations on that input, some transformations on the input, one by one. So that is, it goes from one state to another state because the values keep changing till all the operations are performed. And we expect that if the algorithm is correct, then these sequence of operations will, at the end of the operations, execution of the operations, will give a value or will lead you to a state which corresponds to the correct output for the given input. Here also, we want to move, we want to transform the initial state by a sequence of quantum operations so that after we measure, the probability of the state associated with the correct output will be highest. So that when you measure, you get that state. So here you see there is already some fine line distinction that quantum computing is probabilistic. It is not deterministic. Okay? That means there is a non-zero probability of getting a wrong result. But the purpose of quantum algorithm designers is to make that non-zero probability of the wrong states to be as small as possible. So that if you repeat this enough number of times, a small number of times, the probability gets multiplied, and therefore the probability of getting the correct state, the state corresponding to correct output after measurement is very high, and you are likely to get it. So we now, once again, quantum computing cannot solve all our non-deterministic polynomial time algorithms or exponential time algorithms in polynomial time. So the first one was Deutsch's algorithm. I'll tell you what it is. And then came Shor's discrete logarithm and factorization problem. And then Lovegrover around the same time, just maybe a year later, he proposed the search algorithm, Grover's search. So this is what are known as the triumvirate of quantum algorithms. You'll probably see them in much more detail, but I'll touch upon them a little bit, just very little bit. Some real numbers for the factorization problems. This is what made people sit up, and that's why we are here today. If you have a 50-digit integer, in classical computer, it will take 1 second to factorize. Okay. In quantum time, it will take 1 hour because you have all these very complex operations. These are, the experimental physics, applying electromagnetic field, and all that. Okay. Now, if you increase the number of digits, you'll find that both the approaches can take about 1.5 hours. But very soon, you will find that because classical was exponential and quantum Shor's algorithm is polynomial, you would now see what is the beauty of quantum computing. See over here. So let's look at these three problems very briefly.
Madam, I'm just
Yes.
interrupting once. I'm Kamalika.
Yes.
So, Madam, in the previous slide, you said that 50 and 100. So, approximately how many qubits we will require to solve this?
Yes, I'll get to this. I'll talk a little bit more about Shor's algorithm, just a little bit.
Okay.
Okay. So because this algorithm simply fascinates me. If anybody asks me to talk about quantum algorithms, I just can't resist talking about it. I won't go into the details. I mean, that would take 1 hour. But I will just point out the beauty of the idea. And I will just tell you how to encode it. Okay? Yeah.
Okay.
So, but let's start with a simpler one. It's easier to understand this. Okay. So what did so the first algorithm was by Deutsch in '85, and then along with Jozsa, they came up with this generalization. So Deutsch's problem was as such that you have a function, a Boolean function, okay, of two variables. What I've written here, I'm showing n variables, n binary variables. Deutsch first started with two variables, okay, and so two variables, there are four possible inputs, binary inputs, and you have a function. Okay. Now the function, you have some more information. The function can be either, you're told that the function is either constant, that means for all the four possible inputs, you have the same function value, so you can have two different functions, or it can be a balanced function. That means out of the four, for two of the input vectors, the function value will be 0, and for the other two, it will be 1. So you will have not just two balanced functions, more balanced functions. Okay, I will leave that as a small assignment, small homework to think about. If you have a two variable binary function, Boolean function, two binary variable Boolean function with one output. One output. This is a non-reversible function, mind you. You already know what reversible is. Then, how many balanced functions can you get? So we can represent a constant function like this. That for all the inputs. If now this was okay. So the two input, one output problem that Deutsch considered. There were four possible inputs. Okay, because it's non-reversible. By looking at the output, you cannot say what are the inputs, and of course, so this function is not given to you. It's a black box. Your job is just to correctly tell whether this black box function is a constant function or a balanced function. There can be other kinds of functions, but you have been promised that what you are given, you are not cheated. You are not given a non-constant function which is not balanced. Okay, but you have to check that. Now, what can you do? In classical domain, you have to check all four values, let's say, for all four inputs, one by one, you have to evaluate the function from the truth table and check whether all the values are equal. If it is, then it is a constant. Now, for balanced, you know that two of them are going to be equal. So, you don't need to check 4. You can actually do with 3, right? Any 3. Because you were promised that it's a balanced or constant. If all 3 are same, then you know it's constant. But among the 3, if at least one of them has, if it is a balanced function, then one of them has to be different. So by checking only 3, you can get the answer. So you need to check at least 3 out of the 4. If you generalize this to n binary variables, then you will see that in classical domain, you need exponential time. And that is where Deutsch-Jozsa showed that in quantum domain, you can do this in constant. Okay? So that was the first exponential speed up, or what is known as super polynomial speed up in terms of algorithms. Okay. So what exactly goes in? I will describe very briefly. How am I doing in terms of time? Okay, not too good. Okay, so this is our function. Okay, in fact, if it is an n-qubit function to our quantum algorithm, we start with a system which takes n plus 1 qubits. Okay, and it is supposed to calculate, because of the superposition property of quantum systems. So you had n qubits, you can have 2 to the n possible states, but by Hadamard operation, one Hadamard operation on each of them, you can, at the output, you can get all the 2 to the n states in one step. And after that, you have this special function which is based on this black box function. And what it does is, it's what is called a controlled. It has one, it is something like this. The formula is given at the bottom over here. So this notation, this is called the Ket notation, X, and this notation over here is called the tensor product of the Y. So Y is a single qubit, X is an n qubit system. So when you have parallel qubits, you combine them with a tensor product of the outputs. Okay, the matrix representation states are represented with vectors, and the operations are represented with unitary matrices. So, excuse me. So what happens is that you apply the matrix on the input vector. Okay, so this will be how many states? There are 2 to the n possible states. So therefore, you have n plus 1 qubits. So you will have the unitary matrix here takes n plus 1 inputs and has n plus 1 outputs. So the size of the unitary matrix here will be 2 to the n plus 1 times 2 to the n plus 1, because the size of the state space here is 2 to the n plus 1 here, and the output space is 2 to the n plus 1 over here. So, okay. So the input, if you give the x as the n qubit, whatever input was there for the function, actually you need to just input all zeros, and then you will perform in parallel all the Hadamard operations, so that you get all the 2 to the n steps. And then with one step, you are actually trying to evaluate the value of the function on all the 2 to the n possible input vectors at one go and get the output over here. Okay, so the output is not over here. The output is actually in this extra qubit that you have. Okay, so that is how the function is designed. Okay, so that it is reversible. The input remains unchanged, just like your control, multi-controlled couple gate. So these are more like the control gates, and what you have over here is the XOR of the initial input over here, and the value of the function. This is also a single qubit, right? Because it's a n qubit input, input, single output. So you take the XOR of this, and whatever you get over here is supposed to give you. By looking at this, you will be able to tell in just 2 steps whether the black box function is constant or balanced. So how do we do this? There are 2 tricks actually. One is, of course, the superposition. The other is, so the values, okay, instead of the amplitudes of all the 2 to the n state positions for the n qubits, right, you convert it to the phase. okay, and phase. Okay, so I won't go into the details of the mathematics over here, but let me just point out some of the things. So if you have all zeros in the first n qubits, when you perform Hadamard over here, and this part is through this part also no change is happening, then this is actually what is you have unchanged, and a single Hadamard over here, because it was one, is initialized with 1, will give you this particular vector. Okay, so I have Hadamard on all zeros for the n qubits and Hadamard on the 1 state. All the first n qubits are zeros, and the Hadamard on the n plus 1 of 1, which is 1, and this is what I will get over here. So this is all amplitude. Okay, but what I do is that, you know, if I design this UF as, and this is the function that goes over here. Here you see the value of the function turns out is coming in the phase. Okay, so that is why I think Y here is a little bit confusing. It should have been I or J. So you had 2 to the n different inputs over here, the J states, and instead of the values of the function on all the 2 to the n states, what you'd have is that the value of the function appears as the phase of the superposed state over here. Okay, so how is that going to help us? So that what it helps. So if the function is constant, then after I perform the this particular black box operation, then I do again an Hadamard, so which I expect that all these will return to zeros, and I measure what I have over here. I measure only the first n qubits. If it is constant, then this state that I will measure will be always zero. That I can prove mathematically. I've skipped the mathematics over here. It is mostly algebra. The formula that I gave you, if you expand it. And if the function was balanced, then the measurement will give you a state, will lead to the output state here, one of the 2 to the n possible output states, which is never 0, 0. Okay, so just by looking at this measurement and checking which state it is in, you will be able to tell whether the black box function was constant or not. And how many operations? 1 time step, 2 time step, 3 time steps. Okay, so the trick that Deutsch-Jozsa did was first using superposition, and then converting the amplitude of f of x on all the 2 to the n states to the phase of the states. Okay, and because of that, what happens is when you apply the Hadamard back again, if it was balanced, if it was constant, the phase will be such that there is no phase change. Remember, Hadamard of 0 was leading to 1 by root 2 0 state plus 1 state, and inverse Hadamard would give you back the 0. And if all of them had the same value, then you would have zeros over here. But if it is balanced, that means half of them are zeros and half of them are ones, then you will never get zeros. So that was the trick. Okay. So this is actually the actual mathematics that goes on over here. So f of 0 comes over here. When it is constant, if it is all the same, then it cancels out over here, so you will get the 0 state. But if it is balanced, half of them are going to be one state and the other. So therefore, in the case of 0, you will get the amplitude always in 0 state. In the case of balanced, you will never get it. You can never get it is balanced, you can never get it in 0 state. That is the trick. Okay. So to summarize, if you start again, if you do not allow any failure, okay, in the worst case, if you had the n binary variable, um, uh, I mean the n input, one output function, then you would need to make, this was the homework that I gave you, 2 to the n minus 1 plus 1, so half of them plus 1 extra. Values, you need to evaluate so many. So the exact classical query complexity would take so many steps. How about randomly, guessing, randomly just picking 2 input values and evaluating the function there and checking whether they are equal. If they're equal, you say that it's a constant. If it is not, then you say it's balanced. Okay, just 2 values. Okay, so the probability of failure is less than half. So this is bounded error. But if you do quantum query complexity, then it takes awesome. So this was the first algorithm. Now let's get to the second one, which is Shor's algorithm. So what you see on the screen is a large integer. I think this has around, if I'm not mistaken, about 180, I think 178 digits. This is a large integer. I mean, it's written out in 5 lines. It's not 5 different integers. It's just a sequence of it. I mean, otherwise it wouldn't fit across the width of my slide. And this integer happens to be the product of these 2 large integers. So if you applied the best classical algorithm, it would take x 2 to the power n to the power 1. Whereas Shor's quantum algorithm takes n cubed log n. So here you see again a super polynomial speed up. Okay. Now the idea of Shor's algorithm is very, very nice. So what's the key idea of factorization? So suppose I want to factorize 21. Here the number 21, it's a composite number, it's not a prime. So there are some steps in Shor's algorithm which, quantum algorithm is a complex thing. So you don't want to apply quantum operations on something which you can do in classical domain very quickly and very efficiently. It's only when the classical system is taking a lot of time. As a subroutine, you call the quantum processor and you only give that portion to the quantum processor to get the advantage of speed up. Shor also does that. So it's kind of a mixture. So what is the idea? So suppose I have another integer x, let's say that's 2. And I choose this x integer which is relatively prime to 21, okay, which means that they don't have any common factors. The greatest common divisor is 1. Okay. Now let's see if I raise this x to integer powers modulo the number that I want to factorize. So you see 2 to the power 0 is always 1. 1 mod 21 will be 1. 2 to the power 1 is 2. So modulo 21 is the remainder after you divide by 21. So 2, 4, 8, all of them are less than 21. So it will be the same value. Even 2 to the power 4 is 16, so it will remain 16. But the moment you get to 5, it's 32 modulo 21. That value is 11. If you go to 6, 2 to the power 6 modulo 21, that value is 1. Now notice 2 to the power 0 was 1. Okay. 2 to the power 6 becomes 1. Now you might wonder that, you are likely to guess that after all I'm performing modulo 21. So the output here will be within these 21 values from 0 to 20, right? Okay. So no matter to what power I raise this number x, the outputs are going to repeat. It so turns out that this repetition is periodic. Okay? And it turns out that for this pair 2 and 21, the periodicity is 6. So let's call R to be the period for 2 and 21. What is R? R is the smallest integer for which x to the power R modulo n becomes 1 again. R is the smallest positive integer. Okay. Let's define Y. Now the R is an integer because we chose an odd integer to factorize. Because if it is even, you know, you can do away with all the powers of 2 it has, and you are left with the odd integer to factorize. Okay. So because it's an odd integer, the maximum value of R will be even because it will be this capital N minus 1, which will n is odd, so capital N minus 1 is going to be even. So R by 2 is defined. Okay. So therefore x to the power R by 2 is also a valid integer, and you can compute modulo n. Let's call that y. Okay. So in this case, R was 6, so y was 2 to the power R by 2, which is 3, which means 8 modulo 21, and that gives you 8. Now, if you take the GCD of 8 minus 1 and 21 and 8 plus 1 and 21, this is what you get, which are actually the factors of n. Isn't this a beautiful idea, a very simple idea, which a primary school or middle school student can understand? And why is this working? Very simple. See, what is, because we define R this way and y this way, actually y square modulo n is equal to 1. And what does that give us? That means y plus 1 times y minus 1 modulo n is 0. Which means that y plus 1 times y minus 1 is exactly divisible by n. And what does that mean? That means that the factors of n should divide one of these two. Okay? So y lies between 0 and n minus 1, and this is what y minus 1 and y plus 1 will be, again less than n minus 1, and it is therefore easy to show that the GCD of y minus 1 and n and the GCD of y plus 1 and n are going to be the non-trivial factor set. So it is as simple as that, factorization. So why have we been waiting for Shor to do this? What was the catch? The catch was find R. To find R in classical time, you would have to go on evaluating exponential number of values. And that is what Shor improved. Okay. To answer Amonika's question, I think I have skipped a few slides over here. Let me just try to show them. Will that happen later? No, I don't. I am going pretty slow. So, if you permit, hello, Kapalina, can I just
Yes,
show
ma'am.
this? Yeah. So what you do? How many qubits? That was the question. So how many qubits you take is, so given your n, you choose a number t, okay, such that 2 to the t lies between n square and twice n square. So if it was 21, 2 to the 9 is what you want, and therefore you choose 2 to the 9 is the state space that you want. So you choose t number of qubits. Okay? So you choose, this should have been 2 to the t. Okay, and there's a mistake over here. Okay. So 2 to the t should lie between n square and 2n square. And in this, and t is the number of qubits you will have to take. Okay. So therefore, because I took 9 qubits, I'll have 512 different states. And if I perform Hadamard on all of them, like this, okay, so I start with all zeros. So this is the t number of, so this is how our algorithm is going to look like. This is t number of qubits. You will have 2 sets of qubits, and this is n. So what is n? N is the value to which you're going to, okay, so n is going to be related to, let me get back here. See, I want the factors, okay? So n is going to be related to logarithmic of the number you are factoring. Okay? So, am I right? Yeah. Okay. So you perform, you first perform Hadamard only on the first t qubits. Okay. Then you, so this is what you will get. Okay. Then this is what is actually the main operation that we are trying to do in raising x to the power j. Okay. The x that we chose, which was so x, I'm sorry, x n is actually log of x, not log of capital N. So so therefore, I want to do this in parallel. Okay, raising it to power of j for all possible states over here. I want to do this in parallel. Okay. So when I get to here, okay, at this state, I have for the first t qubits, I have 2 to the power t 2 to the power t states for the first t qubits, and I do a measurement here, which is supposed to give me x to the power j. It will collapse to one of the values of the x to the power j. Remember, there are r possible values of x to the power j. Okay, so one of the r possible ones you will get over here. You still don't know which r. Okay, so you have actually reduced the state space. And after that, so therefore, this is what is happening over here. So notice that for the 0th state, you had x to the I chose 21 and 2. So for the 0th state, the output of 2 to the 1 was 2 to the 0 was 1. 2 to the 2 to the 1 was 2, 2 to the 4, 2 to the 2 was 4, 2 to the 3 was 8, 2 to the 4 was 16, 2 to the 5 was 11, and then 2 to the 6 was 1 again. So you see, I have written it in groups of 6. Okay, I can rewrite this, regroup this as all the ones which got 1, all the ones which got 2. So only 6 possible states are possible. When you measure, it could be either in state 1 or 2 or 4 or 8 or 16 or 11. These are the possible modulo n values that you can get. Okay, so this is what happens. So after you measure, you're actually collapsing to one of these 6 possible output states, and that means you are reducing the state space from 2 to the 9 by 2 to the you are dividing that to 64. Okay, from 9 you are going to 6. Okay, so that is what is happening over here. So once you measure that, then Shor designed this operation over here, which is known as the discrete Fourier transform in polynomial time. From where, from the state over here, you've still got to extract the value of R, and these details, what happens is that, so I'll probably show you this. So before I perform the quantum discrete Fourier transform, only these states which got, so it's, let's assume that it collapsed to the state 2. So only the states corresponding to the values of input states which gave to the J modulo 21 is 2, only those states will have high probability. And after you do the QDFT, then you will have only the 6 states with high probability. And after you do the measurement, it will get to one of the 6 states. So what you will get is, the value. What are these states? These states are related to R by this factor. Okay? You know 9, you know this, but you can determine the actual value of R. You have one of these values. Okay. So you'll have one of these values. I am not going into all these details. Okay. So this is what it's going to look. So you will end up in one of these values, and then from one of those values, the value that you got, and you know that you're trying to find R, what was applied was continued fraction approximation to find the value of R. And once you get R, you can easily find out by the GCD, which is classically done in polynomial time, the factors. Okay? So this is in a nutshell. I think there is a session on quantum algorithms. I took much more time than I wanted to, but Komalika wanted me to talk about this, and I couldn't resist. Okay. So and the third one in the triumvirate is the unsorted search algorithm. I will not spend time on this. So remember, if it is sorted, you can, if you have capital N number of entries in a database, if it is sorted, you can apply binary search, and you can have log n number of steps. You can actually find out whether the given input is actually in the database or not. But if it is unsorted, you will have to actually go through the entire list, which means it is proportional to order. It is ordered capital N. So this is what the condition is. Okay. So if you are given 2 to the n items, then you would take 2 to the n in classical. But in quantum, you don't really get super polynomial speed up. Grover's algorithm. He's an Indian, by the way. From IIT Delhi, and then he was in Bell Labs when he discovered this algorithm. He got a quadratic improvement. Okay. And this algorithm is becoming more and more important every day, because you see most of the NP-complete problems in computer science are related to search. Okay. So, and you have exponential number of possible solutions and you're doing research. So with quantum Grover search, you can not solve it in polynomial time, but you can shave off some of the time. That's all that I'm going to talk about quantum. Okay. Now let's get to the challenges of building computers. So to build, you need theoretical physicists who look at the theory of designing those operations, and experimental physicists to look at the actual systems, such as the superconductor transform based or the ion trap based or what have you, to apply the pulses and get the operations done. In the computer science domain, the theoretical computer scientists come up with these algorithm designs, the mathematicians and the theoretical computer scientists, and do the complexity analysis to find out what kind of speed up you get. And the computer engineers try to optimize in mapping these algorithms onto the physical circuits. Okay. Now the challenge, apart from the ideal circuit, in real circuits is noise. Okay. So one could be gate error. Now let's look at the gate error in CNOT. That can happen in classical electronic circuits also. But as technology has progressed, the amount of error, the reliability has increased quite a bit, and the probability of error has gone down to very low values. Okay. Not only that, if there is an error in a gate, especially if it is a 2-qubit gate like a CNOT gate, so notice that there is an error on the control qubit over here. So if there is an error over here, then it will also affect the output of the qubit, and now you see that both the qubits are errors. And if the target qubit is a control qubit for on the next CNOT operation, then somehow the errors seem to be, getting multiplying or sort of proliferating over the quantum circuit. The other error is the relaxation error. That comes from decoing. So if a quantum state remains idle, if an operation has not been performed on a qubit for a long enough time, then the assumption that it was initialized to a particular state may not always hold. So there is, depending on your technology, there is a time. Okay, so typically for the IBM machines currently, the time is about 50 to 60 microseconds. And there are some very high-end involved and advanced machines where this time has been, the experimental physicists and the technologists have been able to increase this time. So you see that the number of operations you can perform with the current machines is not too many. Okay? And also there is this noise. So you see, when we realize or when we do the synthesis, you take a quantum algorithm. There are some classical functions, just as I showed you with the Shor's algorithm. Checking whether it's odd or even, checking whether it's prime. You have a polynomial time, deterministic polynomial time algorithm to check whether a given integer is prime. And again, it was 3 Indians from IIT Kanpur who gave us this polynomial time algorithm. But there are some other quantum functions like in Shor's algorithm, the discrete Fourier transform. The quantum version is what gave us the actual speed up. Okay. So the classical functions, you can, they may be non-reversible, but you can convert them to reversible functions with the extra lines, extra inputs, so that the number of inputs and outputs are the same. And then you also have the quantum functions. You can have some common quantum functions are used in many of the algorithms, so you can have some module library. But you need so this can give you what is known as non-fault tolerance. You don't actually promise fault tolerance. So this was all technology independent. Now if you bring in technology, then you will have to bring in optimized gates and also bring in fault tolerant quantum logic synthesis. So therefore the gates that you had used over here may not be realizable directly. They may not be the primitive gates, so you will have to decompose those into terms of the available primitive gates. I think Sushin mentioned this, and moreover, not all the primitive gates in the technology may be fault tolerant, so you may have to do some more amount of optimization over here. And this is all at the logic level. Then when you go to the actual physical level, this is where the noise is going to be affecting. So therefore, you cannot do away without quantum error correcting codes. And depending on what kind of technology you have, you will have to actually map the qubits on the physical location of the qubits available to you, the quantum hardware. So this is kind of the physical mapping, the placement and routing, because only if it's a 2-qubit operation, and you are applying an electromagnetic field, it is. Just excuse me, I'll have to switch on my. battery is running low. Just 1 minute. Yeah. So, okay. So today I'm not going to talk about the various optimization that optimization techniques that have been proposed. My group has worked in these areas quite a bit. Okay. Why do we need? So let's just instead focus on the noise part and how that affects the quantum error correction part. Okay. So this one, when you are doing the logic synthesis, it could be technology independent, but when you get to the technology dependent part of the synthesis, you have to take a look at how the qubits are actually arranged. Okay, so this is just one of the ways. And so you can see a matrix of qubits because you have to have access to all these qubits so that you can apply the electromagnetic pulses, the field, to be able to carry out quantum gate operation. And now, if it's a 2-qubit operation, and in the circuit, I might have said that Q0. I'm doing a CNOT operation with Q0 and let's say Q9 over Q8 over here. But it is required that if they are too distant, the field the effect of the state of this qubit, and suppose this is the control qubit, is going to be very weak over here, so it's going to be a very erroneous. So you want them to be nearest neighbors as much as possible. So that means every now and then you will have to keep swapping between, perform the swap operation between two neighboring qubits and then bring it closer. Okay, so these are going to take up more time, and therefore the placement problem is depending on what are the operations and what are, especially the 2-qubit operations, and how far are they. So how do you map these n-qubit circuit onto this 2D array over here, and it could be also 3D. Some of the superconductor-based technology are trying to get 3D, what should I say, 3D organization of the qubits. Okay. Now, what happens is that in terms of quantum error correction, it was shown that you could actually what is called as concatenate. Okay, so one logical qubit is realized as 9 logical qubits here, and each of these are again further 9 logical qubits. So initially, the famous book in quantum computing, the Bible, Nielsen and Schwann's book, they are physicists, and they showed that if you increase the number of levels of concatenation, then the probability of error reduces. We showed in one of the works that that is the ideal case because you have relaxation error. First of all, by that, if you increase the number of concatenation levels, you can see the number of qubits is increasing. The quantum resources is getting, very high. So that cost is very much. And not only that, most of them are going to lie idle. And there, the relaxation error after a few levels of concatenation is going to be much more than the gate error. So therefore, too much concatenation is not going to help. So why do we need this concatenation? There have been different kinds of quantum error correcting codes. We don't have the time, but this has sort of evolved from the classical error correction. So which means that if you have k message bits, what you do is encode this into a larger code word of n bits, and I want to choose n and k in such a way that if in the presence of noise or error, the each code word possible, each of the 2 to the k code word possible. So from 2, k is smaller than n, so the 2 to the k space is being mapped to 2 to the n. So therefore, not there are some empty code words over here. So what I want to see is that if you assume that there is only one error, then in the presence of that error, a particular code word gets to uh, the code words which cannot be obtained from another code word in the presence of a single error. That's called the distance of the code. So there are 3 important codes that came along, a Bacon-Shor code. So the 9 that I showed you comes from the fact that a single qubit is actually represented by 9 qubits. Okay, so a single qubit is logical qubit is represented by this 9 qubits in Bacon-Shor code, and in the presence of this one. So you see 913. That means one logical qubit or one message bit is encoded into 9 qubit code word. Okay, and the distance is 3. That means between 2 valid code words in this 9 qubit, the distance is 3. In the presence of a single qubit, it can uniquely go to so from the erroneous code words, it could have come from only one of the code words. So that is how you can make the correction. That is the idea of this. Steen showed that you don't need 9, you can do it with 7. Okay, and Neil actually showed that you can do with 4, but there are some restrictions over here. Okay. So this is what quantum error correcting codes are, but these need the CNOT gates operations and all that. So for the 9 data, so what happens is that, let's say you have so many circuits over here, you would have to physically map the 9 data qubits over here, and then you have these long distance operations. So I won't go into the details of this. Okay. So similarly, for the 9 physical qubits encoding one logical qubit, you embed it in an array of 7 cross 7, 49 data qubits. You need enough space between them. Similarly, for Steen code of 7 qubits, a 6 cross 8 lattice is used. Okay, and for Neil, you need a 5 cross 5. Okay. Nowadays, we have another major quantum error correcting code called surface code. That also needs quite a number of qubits. Now, so the devices that we have, these are called NISQ, the noisy intermediate scale quantum device. So what is the lesson that we have learned from the quantum error correcting codes are good, and the idea is that you have to place an error correcting block after each gate operation. So you can imagine the amount of quantum resources that you would need to get good results, even if you have a very small original circuit for a quantum algorithm. We did some work taking into account the the relaxation error, and showed that you don't need to actually place QCC blocks after each gate operation, depending on the error threshold that is tolerable for the algorithm that you have. You can sort of trace the given original quantum circuit for a quantum algorithm and place the QACC block at a place where the error probability keeps accumulating after each gate operation, and the level of error is almost approaching a threshold value. So that's where you do the error correction. Okay, that's one approach. But all this is very resource hungry. So noisy qubits are there. So there are no error correction, and you can have only a very few, only just a couple of hundreds of qubits in the intermediate scales. So we need to design keeping this in mind, so that there are a smaller number of qubits and a shallow circuit. Shallow meaning the depth, the number of levels is small. Okay. So this is just, and not only that, as I showed you, the nearest neighbor, the topology. So this is the topology of one of the IBM machines. I think it's the Manhattan IBM Q machine. Okay, and this is the supposedly the 64 qubit machine, which is not available to everybody. But you see that some of the qubits are placed such that they can communicate with 3 neighboring qubits. Some can communicate with just 2 neighboring qubits. Okay. Then there are some other constraints that a qubit can be both controller and target, but some of the qubits are not that symmetric. So all those things have to be taken into account. Okay. So this is what is known as the hardware coupling. So another direction that quantum algorithms have taken, as it is, you have hybrid quantum classical algorithm in this manner for the optimization for a lot of fun. So this was the quantum circuit we've been looking at. Okay, what is done is that you take the output. So this actually not only has the state, but it has some parameters. Okay. So the quantum circuit, the initial circuit is what is called the ansatz. It's a German word for the initial or something to start with. Okay, you perform the quantum operation, take measurement, take the output. Okay, and then there is some cost metric of how good the output is, because the error is likely to be in this real quantum circuit. And so based on that cost, what you do is you update the parameter that you fed into this quantum circuit. And this new parameter is again fed back to the quantum circuit. So and with the new parameter you have a different, the overall structure is the same, but the parameter gives you certain, operations will take this parameter. Maybe the rotation gates will have different angles to rotate, and then you continue with this. So the depth of the preparation step should grow at most logarithmically with the input size. This circuit should not have too much depth, and the number of parameters should reduce. Okay, so the classical optimization is optimization problems can be tackled with this what are known as hybrid quantum classical algorithms. Okay, it has applications in quantum chemistry, quantum machine learning, many more. But let's focus on combinatorial optimization. And this has led to a class of very interesting algorithms which are known as quantum approximate optimization algorithms. I'm almost running out of time. So the first algorithm, these are known as POWA, that was proposed by Ed Parry in 2014, was on an NP-complete problem known as the max cut problem for a given graph. Okay. So what is the problem? You are given a graph, you want to partition the vertices into 2 disjoint sets, the black vertices and the white vertices, and the edges that go between the vertices of the 2 partitions are known as the cut edges. So the size of the cut is the number of edges in the cut. Remember the min cut problem? Okay, finding. So we know in computer science we have the maximum min cut algorithm, which is polynomial time solvable. So to find the min cut of a graph, you have a polynomial time algorithm. But to find the max cut, that is NP. there are problems where you need to find the answer. Not only is it NP, now in classical domain, NP-complete problems have had efficient heuristics. They have also had polynomial time approximation algorithms, which does not guarantee you the optimal solution, but it guarantees close to optimal. So how close it is to the optimal, the approximation ratio, that it can provably guarantee. So if it is two-factor approximation, that is good enough. That maybe your max-cut solution was 10 edges, so a two-factor approximation can give you at worst 5 edges. Okay, so because this is a maximization problem. In the minimization problem, it's opposite. If the minimum solution was for some say minimum vertex cover, let's say 10 vertices, the approximation algorithm in the worst will give you 20 vertices, but in most cases it will give close to 10. Okay, but then there are some problems, some NP-complete problems for which it has been shown that to get an approximation guarantee for to design an approximation problem in polynomial time for these problems with a constant factor approximation, that also is hard. Okay. So max cut happens to be one of such problems. Maximum independent set is another problem. Traveling salesman problem is. The best known classical algorithm, the constant approximation ratio is this. And it is not possible, it has been theoretically shown that it's not possible to approximate better than this. Okay. Maybe some other results are there, but it was shown by Ed Farley that you can solve it by quantum algorithm. Now, how do I convert this graph problem to a quantum problem? Professor Shinkuta mentioned that converting a quantum algorithm to or maybe coming up with a quantum circuit. So you go via reversible circuit. Yeah, but then the formulation has to be done. So the way this is done is comes from again another very classical physics problem, which was basically the max cut problem. I won't go get into I'll just tell that it's called the IZ problem. You can look it up. Okay, I'm really running out of time. So what you do?
No, madam, please take your time. No worry.
Everybody must be hungry. I don't want to stand here too much. But okay, I'll probably need a few more minutes.
Sure.
Maybe 5 or 10 minutes. So what you do is, with each vertex, you associate a qubit. Okay. Now you may start with some partition, some initial partition. If your so partition A will have some vertices. If all the vertices which are in partition A, you initialize those vertices to the 0 state. All the vertices in the other partition are in the 1 state. Okay. Now you apply what is known as the Pauli sigma z operator. So the operation, if you apply sigma z on 0, it remains unchanged. If you apply sigma z on 1, it becomes -1. Okay. So this is what you will get if you apply the sigma z operation on the initial qubits. Okay. Now let's look at an edge in the graph. And we associate an operator, an edge operator in the quantum domain. And this is the edge operator. So if there was an edge between UV, notice what is going to happen. If UV belong to the same partition, then after applying sigma z, both will have the same eigenvalue. Okay? Either both +1, which will multiply to +1, or both -1, which will multiply to +1. And so 1 minus 1 will give you 0. But if they are in two different partitions, then they will multiply to -1 and the value of this operator is going to be 1. So the quantum formulation of max cut, meaning that I want the maximum number of edges such that the two endpoints are on two different partitions, is same as maximizing the sum over all the edges of their corresponding edge operators. And this is what is called the, in quantum mechanics, it's called the Hamiltonian. So for this particular problem, the Hamiltonian of the problem is represented like this, and we want to maximize the Hamiltonian. Okay? So the QA looks like this. Initially, by some classical algorithm, you come up with two times p number of parameters, two groups of parameters, the beta parameter and the gamma parameter. I tell you why. So you have beta 1, beta 2 through beta p, and gamma 1, gamma 2 through gamma. Then in the quantum circuit, okay, you have an initialization phase where you do a Hadamard operation on all the qubits that you have. So it's equal superposition that you feed to the what is known as the ansatz. Now the ansatz operation, what it does, it constructs a state yeah, somehow it's not showing properly. So it is this, no, it's fine. Okay, I can go ahead. It's the gamma beta state, which actually is a sequence of these operations. So it is unrolled. Okay, I've just shown the first one. So it's in the reverse order. Okay, so this is the unitary operation applying what is called the HB Hamiltonian using the beta p parameter, and then followed by UHP followed by the gamma p parameter. Notice it's written in the reverse order because when you so this is your state psi and after you initialize, okay, and on that you apply first this one UHP gamma 1, then you apply HB beta 1, then again HP gamma 2, HP. So that's why it's rigid. So these are matrices applied on this vector, and so these are matrix multiplications that you do to get the final state that you will have output over here. Okay. So this part is called the ansatz, and the reason we call this P and B, this is called the problem Hamiltonian, and this is what is called the mixer Hamiltonian. Okay. So what you do is after you've gone through the P repetitions of this ansatz with the different values of gamma and beta, okay, you do a measurement and you calculate the expectation value like this. Okay. Then classically you optimize beta and gamma such that the expectation value is maximum, and you repeat these two states. So this feedback that you're giving is classical input, not quantum. Okay, so the hybrid model that we saw over here, this is classical input, and in the quantum part there is no. So you stop when you see that the expectation value is kind of not improving anymore. So you have to keep repeating this certain number of times. Now, why? Where is the approximation and where is the optimization? So some promises are the expectation value is a non-decreasing function of the depth p. So the number of iterations that I'm doing is now called the depth of the QAWA, not the depth of the circuit. So the depth of the circuit is actually a multiple of p. Okay, but p is the number of iterations. P is the number of levels of parameters that you go through of this. Okay. As p tends to infinity, this is going to produce the optimal solution. For p equals 1, the QAWA for max cut is produced an approximation ratio more than 0.5, which is the random, if you have done it randomly, for the class of graphs, three-regular graphs. But this is not to be just taken lightly, because even um, the probability distribution generated with p equals 1, that also cannot be efficiently sampled in a classical computer unless p equals n. So this gives us promise that Quava is going to do better than deterministic. In the max cut, it just needs two parameters per layer. Okay, gamma 1 and gamma p and beta p. Okay. So the classical optimizer for these parameters is not. The limitations are that recent results show that this depth of the Quava has to be somewhat more than log n. Okay. And Google recently showed that although we theoretically we said that as p tends it's a non-decreasing function, but they showed in their system we need to do much more in this case. Now noise is the culprit. Actually, noise is what is showing that even theoretically we can have much better approximation, but beyond p equals 3, you are not getting good performance. So how can we? Of course, the solutions are the technology improves, and you can do incorporate some error mitigation. So recently, what we did is, why not try to reduce the noise by making the ansatz smaller? Have fewer gates there. Do some optimization. So the sources of noise are mainly the CNOT gates. So this is the first circuit that I showed you during the introduction. Okay. So this is the ansatz actually for the max cut problem. Okay. The error probability of CNOT gates is about 100 times more than the single qubit rotation gates or the Hadamard gates. So is it possible to reduce some of the CNOT gates without hampering the working of the principal of ansatz? Is there a success rate? We found that you can do this very nicely with some very well-known, very well understood precise techniques. So what we saw that under certain conditions, this was the ansatz we showed for. So this part is the ansatz for the HP with the gamma values, gamma and beta values over here. So the HP, this is the HP takes the gamma value, and the HB takes the beta value. So HP has this a CNOT followed by a rotation, followed by a CNOT, and the HB has the beta value. Based on the beta value, you give the rotation angles over here, and so this is. So the HP that we have, that is actually closely linked to the max cut problem. That we showed that if you do away for certain criteria of these qubits, okay, you can do away with the first CNOT without changing the output. Okay, so there is a theorem. I won't go into the details. When can you remove a CNOT? Okay, and the point is that this ansatz over here is these operators are for edges. So for each edge you have those operators. So what is the ordering of the edges? Okay, so the first one we showed was based on edge cutting. So suppose this was the original graph on which you're trying to find the max cut, and I have done an edge coloring. The notion of edge coloring is that if two edges share a vertex, then they should get distinct colors. So all the edges incident on a vertex will get distinct colors. If you satisfy this, then you get a valid edge color. So for this particular graph with 6 vertices, this is a valid edge coloring. Okay, and you see that I have used 3 colors: red, black, and blue, and the edges are colored accordingly. Okay, so what is done is this is for the first. So what can be done is all the edges in the same color class. You see, they do not share any vertices. So if so the CNOT gates will not share any qubit, so they can operate in parallel. Okay, so all the vertices, all the edges which belong to a same color class, for them you have parallel operation, and you have the first problem handled out. Okay, followed by the next one. Okay, so for the three color classes, you will have three things. Okay, so now the first layer, for the first layer, you can remove the first set of CNOT gates. Okay, so you see these three CNOT gates can be removed, and this is what you get over here. Okay. So now the question is, I have given a graph, I have to do the edge coloring. But the optimal edge coloring problem is NP complete. But the important point about edge coloring as opposed to vertex coloring is that the minimum number of colors required to compute edge coloring lies between capital delta, which is the maximum degree of the graph, and delta plus 1. Just two possible values, but to decide which one, that is also NP. But there happens to be a polynomial time heuristic, and it gives at most delta plus 1 color, so you just sacrifice one color, and by that you get a coloring. So you have delta plus 1 different color classes. So if you had n number of edges, you would have so many color classes. So the number of optimized edges would lie between these two values. So the number of CNOTs that you could reduce lies in this range. The next technique is by depth first search. Okay, so in depth first search, what happens is you are traversing the graph in the depth first order. That means, it's easy to see that the first edge, the tree edge, followed by the second tree edge. So you see that these two edges share this common vertex. So this, if the CNOTs of them will be sharing some qubit. But the first tree edge and this tree edge and this tree edge do not have any common. So they can be operated in parallel. So by this idea, we can also reduce the CNOT gates. And we can show that the depth first tree with a connected graph of n vertices will have n minus 1 edges, and you can actually optimize these many edges, but it is actually going to increase the actual depth of this layer a bit. Okay, so to compare for the same graph, the simple graph that we had, the single edge. So this was the max cuts of the circuit. After edge coloring was performed, you could reduce the CNOTs over here. So the reduction was 3, and the total depth. So those that can be performed in parallel, so these two would count to 1. Okay. Right, all three can be. So the depth here of this circuit is 9. But the depth first search, the reduction in the number of CNOTs is more than the edge coloring, but the depth increases. But even then, we showed that when can the increase in depth be acceptable? Okay, you can have we did some analysis based on the probability of errors, and it turns out there is a parameter which is dependent on the technology itself, and if your parameter the technology hardware parameter lies in it satisfies this condition, then depth of search is going to give you better detection. Okay. For the existing quantum devices, we found the average value of lambda. We need a depth of search will succeed when lambda is greater than or equal to 1. So we found that suffices for all of them. And even after you feed it to the actual what is known as transfilation in terms of the technology mapping of all this, Even then, we found that the number of CNOTs reduced. I'll show the final one. So different graph families for complete graphs with these many qubits. Okay, traditional POWA required these many CNOTs. DFS could reduce them. Uh, okay, right. So here again, after a certain point, we found that DFS was not doing that good. DFS was actually, in fact, you can reduce the DFS numbers even further. Okay, that was the simple DFS. We have another heuristic which does even better reduction. And these are graphs where these are known as heterogeneous graphs. So that what means is that you start with a complete graph, but then you associate a probability. This P is different. This is P edge. That and probability you toss a coin, biased coin, with probability 0.8, an edge will be in the graph or not, and you get certain graphs. So you can generate lots of graphs with varying number of edges, and so you can vary this probability. This is a complete graph is heterogeneous with p edge equal to 1. All the edges are present. Here it's different. So you can see, and second, then we actually mapped these circuits and on the IBM Mind Manhattan and checked on the probability of error. I'm sorry that these figures, so number of vertices, because the IBM machines cannot support many qubits. We could go only up to 12 vertex graphs. Okay, the number of edges is what is going to be there, and we find that so the red one is the reduction, the probability of error, not yeah, this is the probability of error with edge. Sorry, with DFS technique reduction, the scale here is 0.96 to 0.88. The green one was the traditional one, which the original proposer Farid had given. The blue one is the edge coloring machine technique that was proposed. So in all cases, the depth first search can give you guarantee for reasonable graphs with above 0.8. We are working on larger graphs. Okay, so I need to stop. Quantum algorithms, of course, more and more exact algorithms are being proposed. These are challenging to design mathematically. And quantum approximate algorithms, as I said, MIS, PSP, there have been some proposals, but then just proposing the algorithm is not enough. We need to also consider that we have to map them and we have to execute them on the hardware. The error models and various kinds of QCC we have discovered, and particularly in the noisy intermediate scale quantum circuits, the issues are at the logic level, okay, such as reducing QCC blocks, the Ansatz optimization, physical mapping, and also the error decoding. Okay, so even that is a hard problem. And we also need to do technology-dependent optimization of noisy quantum resources, as even these reducing of QCC block, at least the Ansatz optimization and the placement and route and all those things. And another direction is multi-valued quantum logic, because ideally the quantum qubits, they are the 0 and the 1 state represent the ground energy state and the next energy state, let's say for any quantum. But you have a from Bohr's model, you have an infinite number of discrete number of states with lower and lower probability, higher energy states. So multi-valued quantum logic is possible with the current technology. It's just that the probabilities of being in those states are asymmetric. So that's why people right now are struggling with improving the noise scenario for the binary logic, quantum logic, with all these lots and lots of research problems are there. And with this, thank you for your attention. And I don't know whether Paulina and Amrita will permit some time for questions.
Thank you, madam, for enlightening the challenges of building quantum circuits for quantum algorithms. Informative discussion over different quantum algorithms, noises such as gate errors, relaxation error on quantum systems, along with highlighting approaches to tackle present noisy intermediate scale quantum computers. Thank you once again. Now, I would like to request participants to come up with their queries. Please.
Madam, I'm Kamalika again. I just wanted to ask you a couple of questions. So, in the synthesis flow, you have first shown that from the quantum algorithm, we actually need to know the functions that we want to realize. And then we can move towards either reversible, then going deeper into logical gates, and then finally to physical gates. So, with that, what do you think? Do you think that any functions, from quantum algorithms to these functions, all these functions is inherently reversible, but can we represent in terms of truth table or some functional representation?
A truth table, no, because you don't have the discrete thing. But what you will have, so remember all, I mean, I showed the Shor's algorithm a little bit. I showed the Deutsch-Jozsa algorithm a little bit. The quantum function, the UF function, the VX function, those functions that I showed at different stages, those are the functions that I am referring to. Okay, and so if I can go back, maybe I should go back to answer your question, to do justice to this. Okay, so this is what you are referring to, right? The quantum function that you have over here.
Yes.
So so therefore, if you right, let's say this one over here. Is it visible?
Yes, yes.
Yeah, maybe I'll make it a little bigger. So this V, no, the next one actually. Yeah, the Vx over here. So this is the output of Vx. So on the over here you can see Vx applied to the state J. I mean this p qubit going from 1 to 2 to the 0 to 2 to the t minus 1, and the state K from 0 to 2 to the n minus 1. Okay, so this function over here is actually the heart of the quantum algorithm design. Okay, and then if I move on further, so these are the functions that I have, and then moreover, if I go back to even Deutsch-Jozsa, okay, look at these. So these are the functions. Okay, the Hadamard function is a function. I mean, operation is a function. Okay, because this is the the mathematical form for it. Okay. Now, some of these operations have truth table. I mean, you have the unitary matrix representation more, rather than the truth table operation. If it is reversible, of course, you are in the domain. You don't have the complex numbers. Okay. You may have unitary matrices. So, for example, let's look at the rotation gate. Okay, the rotation gate. Do I have the rotation gate here? No, I don't, unfortunately. Okay. Well, there's e to the power minus I theta. This theta by 2. Okay. So how do you represent that as a truth table? Okay. So what should be done is that, or what has been done, the FTQLS work that we did, we identified certain types of typical, so the rotation gate, unitary matrix operation, and what would be the realization in terms of whatever uh, uh, gate library you have. Okay, so those things come into play. Is that, have I been able to answer?
Yes, ma'am. Yes, ma'am.
Yeah. Okay.
Thank you. Thank you very much.
Thank you, ma'am. Now, I would like to request our Professor Choikot Maiti sir, HOD of our department, Computer Science and Engineering, JIS University, to felicitate our speaker, Professor Shushmita Shurkole, madam. Sir, please.
Ma'am, I'm little bit interrupting.
Oh yes,
Ac-
please go ahead.
Actually, ma'am, once one of the participant asking that, ma'am, please suggest which specific topic is good for my PhD.
What is your background? Is it
Ma'am, it is
computer
not,
science?
ma'am, actually, Ravi Tiwari, can you speak directly, talk to ma'am? Hello, Ravi Tiwari, are you there?
He's
I think, I think she left.
yeah,
He
yeah,
left.
yeah.
Yes.
Please unmute yourself. Please unmute yourself. Or you can write in the chat box. Are you from?
Madam, I have a question. My name is Suman Lahiri, and I belong to a completely
Sorry.
different line.
Yeah,
And
but I
depart-
think Ravi, we were answering Ravi
Okay.
Tiwari's. I'll take your question. Just bear with us. I'm really sorry. I apologize for taking, 15, more than 15 minutes extra.
No, ma'am, no problem.
So, Ravi Tiwari, are you there? Otherwise, we can pick up. Oh, you have MTech in VLSI design specialization and BTech in what? He's writing in the chat box. Maybe there's some problem. What is your BTech in? Electronics or computer science? Okay. You see, the synthesis issues, the optimization issues, they involve more of algorithms. Okay. But still, it's good to have this background. Um, Logic level, and also quantum logic level optimization, different gates and all that. You need to prepare your background in the quantum. So if you're interested in logic synthesis optimization techniques, you can do that. But I would suggest that you take a proper course in design and analysis of algorithms. Optimization means that you would have to apply algorithms. Okay, so with that and your electronics background, I'm also from electronics background, and then I shifted to computer science. But then I saw in VLSI design, the domain knowledge helped me to abstract and then apply the computer science techniques. Does that answer your question? And then we take Mr. Lahiri's, Dr. Lahiri's question. So yes, Mr. Lahiri, please go ahead.
Yeah, good afternoon, madam. I'm from the Department of Management Studies. I have a very different type of question for you. I just trying to correlate. So maybe it's a little out, but I was wondering because, when we look at some of the aspects in the base of the pyramid energy consumption market, there are multiple variables. The consumption of energy is related to education factor, health factor, livelihood factor. So, but we don't really know how this is acting at the minute level, how they are interacting. So if I relate to the quantum inputs, so, and when we are talking about n inputs in qubits, and then it is obtained as one function f, then one question in my mind is this n variables in terms of food, health, livelihood, remoteness from the center of operation. and their superimposition in the quantum state, does it can it be solved by quantum algorithms? Is that a way of going forward? Because this is a very complex equation, I believe. I'm just trying to correlate.
So, okay. Well, I'm definitely not an expert in
So
this
there,
area, but
there is a
from
function.
what I understood is that, you know, this is
Pardon?
in my I don't know whether this is visible. When I talked about, are the slides visible? No, not. I stopped.
Not visible, ma'am.
Yeah, I stopped showing. Yeah, now I think it should be visible. Right?
Yes,
so
it
as
is
you
now
see, the application areas are wide spectrum, are from a wide spectrum. Quantum chemistry. So what I gathered your second sentence was energy. Okay, so in chemistry, in quantum chemistry, energy is an important. Anything that we do, any design, any evaluation that we do, whether you design a bridge or an algorithm or a chemical system, there is an optimization involved. Okay, so there are different types of optimization. The combinatorial optimization are discrete in nature. In quantum, it is analog in nature, and even for analog systems, there are quantum algorithms. In fact, quantum annealing comes from that background. Okay, is kind of related. So what you need to do is look at the multivariable function, and I assume that this is a continuous function with continuous variables. Try to map it. Try to map that optimization problem into the analog domain quantum optimization problem, if it is possible, and then check how you can design, you can make use of or apply quantum operations to obtain either the optimal solution or a near to optimal approximate solution. Okay. Another way is the quantum machine learning. A lot of classical machine learning is applied to many of these optimization problems coming from various domains, including energy management and all that. So you can apply quantum computing to solve complex optimization problems. That is what I'm trying to highlight. There is possibility. I wouldn't go into, so if you want to go into the quantum mechanical microscopic level of the system to optimize, then one word of warning is that the size, if you want to, so again the level matters. If you want to minimize energy at the macro level, then you have a different problem. If you want to minimize at the, so you formulate the macro level problem, even that optimization is a difficult problem. You can try to find quantum algorithms to solve it. And at the micro level, what will happen is you will actually be trying to do the simulation. Right? In quantum chemistry, what happens is people do simulation or emulation with the quantum system and try to gather the information about the optimal solution or the near optimal solution. I don't know whether I've been able to answer what you are looking for, but there is scope. There are physicists and people from chemistry who are working in this area. A lot of real science people, basic science people, they have to. I mean, that is the whole purpose of Feynman proposing that, because that's where they will be getting started. A lot of supercomputing efficient algorithms evolved because physics and chemistry needed large scale computation.
Madam, that brings, Madam, thank you very much. That brings to my second question very quickly because time is an issue. So if I look at the, the chart flow where you have mentioned about the
I
different
think
levels.
I think I need to switch my network connection. There's
Okay.
a bandwidth problem. Just allow me a minute.
Yeah, ma'am.
Hello?
Yeah, yeah, ma'am.
Yeah, I'm back. Yes, thank you for your patience. Yes, please go ahead.
Your answers gave me some insight. The second question is this, that when you are mentioning about the flow chart, coming to the classical optimization and quantum optimization and algorithm, and then coming to a physical level. So do
Yes.
we need to design our physical circuits when we are designing, even for energy consumption for the rural
No,
market
no, no,
at
no,
macro or
no.
no, it is not
No,
necessary.
no.
Okay.
I mean, this is very expensive. Only a few
Yeah.
people are doing it. It's very complex. Even in India, the efforts are being made, as Professor Gupta. But so, as to the best of my knowledge, only up to five. Was it 5 or 3 qubits? It was possible. Yeah, all over the world, I mean, this is a big challenge. So I don't think it's wise to focus on that. What you need to do is look at what is available and how you can map efficiently on your available resource. Okay, so that also
Okay, ma'am.
has challenges.
Okay, madam. Thanks a lot. Thank you very much.
Thank you, thank you.
Thank you, ma'am, once again. And now I would like to request Professor Shoykot Maiti sir, HOD of our Department of Computer Science and Engineering, to felicitate our respected speaker, Professor Shushmita Shurkole, madam. Sir, please.
Thank you so much, ma'am. Thank you so much, Sushmita, ma'am. It's really a wonderful means to hear from you, especially in this particular field. And this field is quite interesting. So it's a, now I'm sharing my screen. It's a token of love, regards to you. Please accept it, madam, from
Oh yes,
GIS University.
I'm honored and
Thank you
I'm
so much.
very glad to accept this. Thank you very
And a
much.
digital memento for you all.
Okay, thank you very much.
Thank you, ma'am. Thank you so much for giving your precious time to us. Thank you.
And
Over
thanks
to
to
you.
all the participants for bearing with me for much longer than they had planned.
Thank you, ma'am. Thank you so much. It's over to Dr. Banerjee, please.
Thank you, sir. And thank you, ma'am. This is the effect of your attraction of the talk that you have delivered to us. That keep us with this, that keep us attached with this talk. Thank you, ma'am, once again.
Yes,
And
I would hope that at least few of you would get enthused, and after this workshop where there are speakers after me with more details, you can get interested in doing research in this area.
Thank you very much, madam.
Yes, thank you. Wish you all the best.
thank you, ma'am, for your kind blessings. Now, in this way, this is end of our session 2. We are going to start our next session from
2:30.
2:30, and definitely we are going to have another quantum computing track with impact of quantum computing in cryptography. So please join with us once again at 2:30 p.m. Thank you, everyone.